This week, let's cover multivibrators circuits, and it's chapter number 7 that I'm providing on Canvas, flip-flops, registers, and counters. This is the learning objectives for the week, and let's start with the motivation. So with a simple gate, what you are familiar so far, any combinational logic circuit has a defined output state. So if this is an OR gate, you know when you put 0, 0 that you get a 0, and a 0, 1 you get a 1, 1, 0 you get a 1, so forth and so on. So there is no ambiguous output state. But however, if we alter this circuit slightly different, if we do something like this, now what happens? What happens if I start connecting the output of my circuit to the input? And this is called feedback. Well, when A is 1, it's pretty obvious. This is an OR gate. Your output is going to be a 1, no matter what you have on the other pin. But if your A is 0, then what is the output? Well, instead of a question mark, we're going to use or start using the word latches. And latch means that it maintains the last state. So if A was 0, it keeps that 0. If A was 1, it keeps that 1. So let's see different types of circuits that employ this feedback method that we call multivibrators. We have bistable circuits, monostable, and astable. Inside of bistable circuits, it can hold stable in one of the two possible output states, either 0 or 1. Monostables can have only one stable output state at a time, and you can have the other one happening but very momentary. And then you have the astable, which does not have a stable state, so it just oscillates back and forth between 0 and 1. Let's start with those ones, because those are the simplest one. So if I pick up a NOT gate and I connect the output to the input, so if I do this feedback, what's going to happen is your circuit is going to oscillate. It's not going to be either 0 or 1. It's going to oscillate between 0 and 1. So the result is a high frequency, normally several megahertz oscillator if implemented with a solid state inverter gate or a semiconductor. Let's go over bistable circuits. So a typical bistable circuit is the set and reset latch, and this is done by connecting two NOR gates together, and then you feedback the output, or you connect the output of one NOR gate to the input and to the input of the other one, and vice versa. And what's this going to create, this is the truth table, is that when you have a 0, 0 on your inputs, it's going to latch or have the previous value that you had on the Q. Or what did you have at the inputs of your SR latch. But if you have a 0 and 1, your Q, your output is 0. If you have a 1 and a 0, your output is 1. And if you have both 1s, you get a 0. You always have this Q and Q naught. So Q naught is going to be the opposite of Q all the time. So let's look and dive in on this SR latch a little bit more. So this is the schematic, and then we can have a symbol for that SR latch. So notice here that on the symbol I have the inputs and the outputs represented, the S and the R, and then the Q and the Q naught negated to know that this is the opposite of Q. So we went already through the truth table, and there is one more important thing to know that we're going to call illegal state. This is not an illegal state, you can go there. The difference is that because it's a 0 does not make sense. So I already have, so when set is 0 and I'm resetting the value, I get a 0. When I'm setting the output 1, I get a 1. But when I have both 1s, I'm getting the same behavior as if I was resetting. That's why it's called an illegal state. It's a state that you want to avoid if you're trying to take some actions out of this SR latch. So let's go over the gated SR latch. So sometimes it's useful to have a way to turn on and off your circuits. So notice here that the gated SR latch builds on top of the SR latch. So I have here the SR latch where it was sensitive to the inputs, but now notice that I put two AND gates here. I still have my S and R, but I'm connecting to enable, and the enable now is making sure that the SR latch only works when my enable is equal to 1. So if my enable is equal to 0, I can put any values on the SR that is going to keep the previous state on the output. But if I put enable equals to 1, this bottom part here of your table works exactly as an SR latch. So I still have that illegal state, we're calling it illegal state, but we give one more fixture to our circuit, which is the ability to enable or disable. This is the symbol. We have the S and R, and then the enable, Q and Q naught. So let's go over the delatch. So what if I want to get rid of these illegal states? What you do is you connect the SR inputs together through a NOT gate, and now you no longer have illegal states. What happens is for 0, 0, you memorize the previous state. 0, 1, same thing, it makes sense, your enable is 0. But if your enable is 1, notice now that Q is going to follow the input D. So if D is 0, Q is 0. If D is 1, Q is 1. And Q naught is just the opposite of Q. No illegal states, and this is the symbol. I have the D, my input, the enable, turn on and off, my delatch, sorry, and then Q and Q naught. So this is the differences, or these are the differences between the gated SR latch and the D latch. So notice that they kind of build upon this SR latch, and then I include that turn on and off ability, so I get the gated SR latch, and then I give rid of that illegal state and I get the D latch. So just different variations of circuits that you have. These are the symbols. So notice that you start with these gated SR latch. I put this gate to connect S and R together, and I get my D latch. Edge trigger latches flip-flops. So far what we have been doing is that we have the latch response to the data inputs SR or D only when the enable input is activated. And let's just go and see practice a little bit the waveform that you're going to see out of the latch. So let's say that I'm going to feed the D and the E, so this random signal and D and this random signal on the enable. And what's going to be the Q? So notice that while the enable is 0, my Q is 0. So nothing new here. I'm latching. I'm on this condition here, on this top of the first two conditions of my truth table. But when the enable goes to 1, now notice that Q is following D. And the minute that I put enable to 0, my Q is going to latch to the previous value, which is 1. And then Q keeps 1, does not matter what happens to D. And the minute that enable gets to 1 over here, notice Q following D. It's doing the second part of your truth table. The minute that enable goes to 0, latches to the value, so it was a 0, so it latches to 0, memorizes that value. And then just the third example, same thing, enable goes up and Q follows D, enable goes down, and my output is 0. So this is the typical waveform that comes out of a D latch. So Q follows D. What if I don't want that to happen? What if I want to detect just transitions? What if I have a signal and I want to detect the positive edge of a square wave, or even the negative edge when it goes down of a square wave? I cannot use a D latch because the Q follows D on a D latch. So this is when we have the edge trigger flip-flops, and these are going to be sensitive to transitions. And let's see an example here. How do they work first? So I feed the D and the E over a positive edge trigger flip-flop. So positive is focusing on the transition from 0 to 1. So Q is 0, enable is 0. The minute that enable goes to 1, notice that Q takes a picture of that value and gets 0. And then no matter what happens to D, Q latches to that value. On the next transition, same thing, 0. And on the third transition, here the value was 1, so it latches to 1. So I'm able to detect the transitions and memorize those values. A negative edge works exactly the same way, but now I focus on going from 1 to 0. So Q is going to be 1 because D is 1. Here, same thing, Q is going to be 0 because D is 0. And here keeps 0 as an output. So what circuit does this edge trigger? Well, the edge trigger builds on two D latch flip-flops, one that we call master because it's the first one that you connect here, and another one called slave, but there are two normal D latch flip-flops, and you put a couple of NOT gates here to connect the enables together, and now have a word that we call clock. So instead of enable, we have a clock. And this is the symbol, so notice that it's very similar to a D latch. The only difference is that we have this triangle here indicating that now we call this clock. And if I look at the negative edge, it's exactly the same thing, same configuration, just one less gate. I don't have the NOT gate over here, and this circuit is going to detect negative edges. The symbol is similar. I have the triangle, but now this time I put a negation, and this tells me that this is a negative edge trigger flip-flop. Let's look at the JK flip-flop. So another variation is a JK. So notice that it's a modified version of an SR latch. So notice here that 0, 1 gives you a 0, which is the value that we have here. 1, 0 gives you a 1. And the good part is that, again, you don't have that invalid or illegal state. Now if you have 1, 1 on your JK, it's going to toggle back and forth, which is pretty cool. And then all the other states are going to latch. So JKs are very useful because you can pretty much implement all the other circuits with, or all the other flip-flops with JKs. Alright, so this is your circuit for your JK, builds upon a positive edge trigger flip-flop, and you put here your SOP, this circuit over here, and now you have a JK and a clock. Summary of terminology, so we start by covering a basic latch, which is level sensitive. We connect them together with an enable, we call here clock, can also be called clock, then we call it gated latch. And now there are two variations of this one, the gated SR latch or the gated D latch, where we put the SR connected together. From a D latch, I can build a positive edge trigger flip-flop by combining them in this master-slave combination, and they can be negative or positive edge trigger. And we finally, if we pick up those positive edge triggers and we connect with some circuitry, we can do JK flip-flops, and another family, T flip-flops, where we change the circuit connected to the positive edge trigger, and you get this T flip-flop. So applications of all these knowledge. It's widely used in microprocessor architectures for registers, memories, counters, or state machines. It's used as a shift register, so I can put information on my in, give some clocks, and that information keeps being shifted between each flip-flop here. And counters, I can use them to do exactly that, to start counting, and they can be synchronous or asynchronous. So notice that the asynchronous, the clocks are not connected together, while the synchronous, all the clocks are connected together. So you can do a lot of stuff with these flip-flops. They are just memory elements, they retain information, and that's what we're going to do on the next videos, practice on how to use these with circuits.